Hey guys, welcome back to another video, and today we're going to be solving the Leet Code question course schedule 2. Alright, so let's just go over the question real quick. Alright, so we have a total of n courses you have to take, labeled from 0 to n minus 1. So some of these courses have prerequisites, so let's say you have 0, 1. What that means is in order to take course 0, you have to first take course 1. Alright, so then we're given the total number of courses and the list of prerequisite pairs. So then we need to return the order of courses we need to take them as. Okay, so there may be multiple correct orders, you just need to return one of them. And there are a few cases where it is impossible to finish all courses, and in those cases we just return an empty array. Let's quickly look at an example to understand what this actually means. So over here we're given 4 courses, so 4 is the number of courses, and these are the pairs of prerequisites. Alright, so what is our output going to look like? So let's just look at class 3. So to have class 3, you must have finished class 1 and class 2. So now let's look at class 1 and 2. So to finish either class 1 or class 2, you must have to finish class 0. So obviously our first class is going to be 0. And then we can do either 1 or 2, it doesn't matter. But we need to finish both of them. And only once we finish 1 and 2, we can go on to doing class number 3. Alright, so now we're going to first go over the theory behind solving this question, and then I'm going to use Python in order to implement a solution to this. In order to solve this question, we're going to be implementing something called a topological sort algorithm. So what this does is it takes a directed graph, like for example this one which we have over here, and we're going to return an array of the nodes where each node appears before the node it points to. So what does that actually mean? So over here, so we have this graph, and this is one of its topologically sorted order, and this is actually an accepted one. So what does that mean? So let's say we look at the node A, and we have A over here. So we need to look at what is pointing to A. So only B is pointing to A, and what that means is B has to appear before A, and it does, so that's fine. So similarly, let's look at C. So we have C over here, and what's pointing to C? B is pointing to C, and so is A. So B and A have to be before C, and they are. B is over here, A is over here, and they're both before C. So let's just go to E. So we have E, and for E we have A and F pointing to it. So in this case, A and F have to appear before E. So we have A over here and then F over here. So similarly, let's just assume that each of these alphabets represents a class, one of the classes, and we can implement the same logic to solve this. So let's see how we can actually form a topologically sorted order from scratch. So in order to do this, we're going to be implementing a queue, and we're going to start off by looking for the nodes or the edges which have no arrows pointing to it. So we have B. Now we're going to add that to our queue. So we're going to add B. And what else do we have? We're nothing. So, and then we also have D. So there's no arrows pointing to D. So we're going to add that to our queue. Now what we're going to do is we're going to pop out the first element. So we're going to pop out B, and then we're going to add that to our topologically sorted order. So we're going to have B over here. Now that B is in our topologically sorted order, we're just going to cross out B over here. And we're also going to cross out all the arrows going out from B. So we're going to cross this out, and we're also going to cross this out. Now that we crossed out all the arrows pointing from B, we're going to look for other nodes which are freed up. So in the sense that we need to look for nodes which now have nothing pointing to it. So do we have anything like that? So let's look at C. So there's something still pointing to C, so let's just leave that. But if you look at A, now that we crossed this arrow out, there's nothing pointing towards A. So now we're going to add A to our queue. So now we have A. And similarly, so then again, once we added A, now we're going to pop out whatever we have in the queue again. So we're going to pop out D, and we're going to add that to our topologically sorted order. And similarly, we're going to cross out D and the arrows going out from D. And now we just see if anything has been freed up. But there is nothing which is freed up because of this. So what we're going to do is we're going to pop out the other element inside of our queue. Alright, so now we have A, and we're going to cross this one out, and we're going to add that to our answer over here. And similarly, what we're going to do is we're going to cross out A and all the arrows coming out of it. So we have this one over here, this arrow here, and also this one. So that should free up quite a lot of stuff. So let's look at E. Well, there's still an arrow pointing to E, so we can ignore that. But we have F over here, so there's nothing pointing to F, so we can add that to our queue. And similarly, there's nothing pointing to C, so we can also add C. So now we're going to pop out this element. We're going to pop out F, add that to our topologically sorted order, and repeat the same steps. So we cross out F, and we cross out the arrows from it. And so now we have E and we have G freed up. So I'm going to add that to our queue as well. So we're going to add E and we're also going to add G. Now again, pop out C over here, add that to our answer. So we have C, cross it out. There's no arrows coming out from that, so we're fine. So I don't have space, so I'm just going to continue it from here. Okay, now we have E. There's nothing there, so just pop it out and then add that to our topologically sorted order. Then we have G, same thing, pop it out and then just add that to our topologically sorted order. So the order we got finally is B, D, A, F, C, E, G. So let's just quickly check if this is valid or not. So let's just look at G, for example. So F is pointing to G and F is before G. So now let's just look at F. So A is pointing to F and it's before F, so that's fine. Similarly, let's just say E. So A is pointing to E, and so is F pointing to E. So they both, A and F, need to be before E, and they are. A is here, F is here. Let's just look at one last example. Let's say C. So B is pointing to C, and A is pointing to C. So B is before C, and so is A. So this is an accepted answer, and this is a correct way to do it. So now what we're going to do is we're going to take our question. So in our question, we have a list of lists, and we're going to convert that to a graph similar to this one. And then what we're going to do, we're going to apply the same algorithm on that graph, and then we're going to get a topologically sorted order like this, which is going to be our answer. So let's see how we can do that using Python code. Before I start explaining the code, I just want to explain this one term called in degree. In the explanation I just gave, I kept referring to the number of arrows pointing towards a node. And that is nothing else but the in degree. So there's two arrows pointing towards a node. It has an in degree of 2. And if it has 0 arrows pointing towards it, it has an in degree of 0. Okay. So now that we understand that, we can start with solving this problem. So first what we're going to do is we're going to import some stuff. So from collections, we're going to import a queue, and we're also going to import a default dictionary. So you might be asking why we're using a default dictionary instead of a dictionary, like the inbuilt one in Python. And that's because the main difference is basically in a default dictionary, when you try to access or change a key that's actually not there, in that case, the default value will automatically be given to that key. So we're just going to create our graph, which is just going to be an object of the default dictionary. So default dict and then list. Okay, so now that we have this, we need to have some sort of way to calculate the in degree of a node. So to do that, what we're going to do is we're going to create a list with zeros, and it's going to have the same length as the number of our courses. So num courses. So if our the number of courses we have is 2, the list of our in degree is going to be a length of 2, so 2 zeros. Now we're going to set up our graph. So what we're going to do is for, so pre is going to be the prerequisite classes, and then I'm just going to call final as being the main class. So for that, in our prerequisites over here, and what we're going to iterate through all of them, and to our graph, we're going to add final as a key, and we're going to append the pre value. Okay, and similarly, and one more thing we're going to do is we're going to increase its in degree value by 1. So in degree of our prerequisite class plus 1. So we're going to increase that by 1. So now we're going to prepare our queue, which has 0 in degrees. So our queue is going to equal to dq, and x for x in range, and then num courses. And then we are also going to put a if condition. So if in degree x is equal to 0. Only if that node has an in degree value of 0, we're going to add it to our queue. We're also going to initialize our topological sorted order. So this is going to be our final answer, and it's going to just be an empty list in the beginning. So now we're going to put this inside of a while loop. So while length of q is not equal to 0, we're going to keep going inside of our loop. Now what we're going to do is we're going to pop out whatever element we have inside of our queue. So we're going to call that the node, and q.pop left. Yeah. And then after we do that, we need to append our node to the topological sorted order. So it's the same steps as we did before. So we're going to append it to our topological sorted order, and we're appending the node. Okay, so what we're going to do after that is we're going to iterate for the neighbors inside of graph node. So the neighbors of that node, and what we're going to do is we're going to reduce the in degree by 1 for all of its neighbors. So in degree of the neighbor, and we're going to decrease it by 1. And one more thing is, if the in degree of the neighbor is equal to 0, then in that case we're going to add that to our queue. So q.append, and we're going to add the neighbor. All right, and finally we're going to return this. So this is going to keep going until our queue is empty. So we're going to return our topological sorted order over here. And one more thing is we're only going to return it if the length of our topological sorted order is the same as the number of courses. And if that's not the case, we're just going to return an empty list. All right, so let's submit this. All right, and as you can see, our submission did get accepted. And finally, do let me know if you have a better solution to this, and do let me know what you thought about this video. And finally, don't forget to like and subscribe. Thank you.